before this, these telescopes were giving only upper limits.
Correct.
So they were not able to reduce the noise properly, although they observed for many, many years. So yes. Yes. Right. So the foregrounds are have gone into the noise in some sense.
Yeah. Thanks.
I think no more questions. Do you have any questions? Please ask. Okay, then I think the next session, next tutorial by Divesh Jain. Divesh, please start.
Yeah, hi, I'll share my screen.
Yeah, sure.
Is my screen visible?
Yes.
Right. Okay. So yeah, hi everyone. In the previous tutorial, Varun had shown you how you can analytically model reionization, and you can solve for the ionized fraction of hydrogen as a function of redshift. Now, this method allows you to calculate global parameters. That is, you only get one value of mean ionized fraction of hydrogen per redshift. And if you integrate over all redshifts, you can calculate the optical depth. But we cannot use this model still to ask the questions like if the reionization was a patchy process or not, or whether at any redshift was it, we cannot see the effects of if we have low mass halos or high mass halos. We cannot see the effects of reionization on the ionization map through the analytical model. Now, to answer these questions, we would like to calculate power spectrum and generate ionization maps. And for this, we'll need to calculate fluctuations in neutral hydrogen. Now, Tit has already discussed the formalisms one can employ to calculate these fluctuations. One was the excursion set approach, and the other one is the photon conserving formalism, which was developed by Tit and Asim in 2018. And we'll be mostly spending our time to familiarize ourselves with the software script, and we'll try to generate ionization maps and power spectra at different redshifts and minimum halo mass parameters. So yeah, let's start into it. Just one more thing, if you have a doubt, please feel to interrupt me during the session. It would be okay to just send a text or just unmute yourself and interrupt me. So yeah, let's get started then. You must have received a zip file named EoR tutorial. What you do is extract it, and once you have extracted it, you'll see two PDF files and two Python notebook files. Out of this, the tutorial 1 was already covered by Varun yesterday, and today we'll look into the tutorial 2. So let's open the second tutorial PDF. So this is what your PDF looks like. And in the second step, we have mentioned click on this link. So yeah, click on this link to open the Google Colab platform, or you can copy this link to and paste it in your favorite browser to get Google Colab running. So with this link, you'll land up on the Google Colab platform. Now, this platform is really interesting if you want to start coding. Google Colab is basically an online Jupyter notebook, and it has its own virtual machine. So you don't have to spend resources on your own machine and to learn coding or get into data science. Just log into Google Colab and you can get started. Let us see how you can upload the Python notebook that we have provided to you. Go to upload, choose file, and go to wherever you had extracted the notebook files, and click on EoR tutorial 2.ipynb and open it. So it was a success. So in general, a Python notebook file like this would consist of two parts. One will be the code cells, another will be the text cells. Now these are where I've written descriptions are the text cells, while the places where I've mentioned the code are called the code cells. You can click on these icons to compute or execute these sets of codes. And it is upon you how you can use these code cells and text cells to make your Python notebook as friendly as you want. Here, we also have mentioned some troubleshooting tips, which I thought would be helpful to you if you are just getting started with the Jupyter notebook business. So let's start with today's tutorial. Before starting with how we'll utilize script, first we should know how to install script. And in this process, we'll also download the dark matter distribution files that will be required for our tutorial exercises. Just a note before that too. As I had said, that Google Colab is basically a proxy to your own machine. So you can find the concept of folders. Here it is connecting. And you can install whatever you want to install in any of the folders. So right now we are in the content folder, and this will be our work area. Now we'll be downloading all our files here, and remember that this setup is temporary. So if you close this page and again log in back, any files you have downloaded will not be available for reuse. You do have a method to save it, but we are not employing that today in this tutorial. So let's first see how we can install script. We go to the content folder, and inside the content folder, we first install the dependencies of script. Now, script has two dependencies. One is NumPy, which is pre-installed by the Google Colab, and the other is FFTW3. And you can use apt-get install to install the FFTW3 library. And next, let's ask Python to clone the script code from its Bitbucket repository and run this cell. So here the cell is running, and the green marker shows where the interpreter is at. And right now it is installing the FFTW3 library. Remember, when you run it on your own machine, there might be much more terminal outputs, but I have transported all the standard outputs to /dev/null. So the terminal is clean for me right now. Unless an error pops up, that will come up here. And now once we have cloned this script repository, let's go into the script folder and use setup.py installer to set up a script module so that we can use script modules and its functionalities for our activities today.
Hi.
Hi.
Hello. Yeah. So if I'm running it in my computer, so should I, like, I'm getting some errors if I run this git clone. So is there anything I can do to
What
change
kind
it?
of errors are you seeing?
It says that there is no file or directory saying content.
Okay, so are you running it on the Python notebook that we have provided to you?
Yes. Yes.
Okay, so have you ran the first code cell %cd/content?
Yeah, it is there. Yeah, it's already there, right? Yeah.
And it is already run, right?
Yes.
And when
No, no,
you
no, no. So what they are saying is that content directory is not there in the directory where I have copied this notebook.
you parent, so it is not required for you to copy the notebook. Okay. Uh, um, let's see. Um, so you went to file, went to upload notebook and chose file to
Uh,
start the whole process, right?
I understand, but what I'm telling is like I directly opened it in my Jupyter notebook in my system.
Okay,
So
okay. So
then
yeah,
it did
this
not work.
particular notebook has been compiled to work on Google Colab and not.
Okay, fine, fine. Okay,
So,
then I'll do like I mean I'll upload it in Colab only. Okay,
yeah.
sure,
So
sure,
so that like everyone becomes platform independent. So
sure, sure.
we have used Google Colab platform.
I just want to add something like did the slash content with the directory are you using right now? So that will help. So,
I'm not understanding.
so actually
Figure it out.
instead of using content, you can use your directory where
Right,
these
right,
things
right.
are copied in your system.
Correct. But
Okay, okay. I'll change the address of the directory then.
right, but the
Yeah.
commands which will come up eventually are set up according to the Google Colab platform. So I think it's better
Yeah,
to
sure. All these things has changed.
yeah, you have to change all the paths then. So yeah, we have already installed script and ran the setup.py installer. And now the script functionalities are available to us in form of Python modules, and we can just write import script at any time, and all the functionalities will be available to us. Once this is done, we are good to go from the side of installing script. Now, secondly, what we have to do is use snapshots, which I generated from a 2LPT code called music. And I'd already generated these snapshots and uploaded to a Google Drive. And what we'll be doing is downloading those snapshots from the Google Drive links. So first I create a work area where I'll be storing all the snapshots. And this change directory is to just set up the path. Sometimes it shows errors. That's why I have specified which path we'll be using. And then we make another directory called script files. And this folder will contain all the data products of script code run. So let's run this. And now we'll be downloading snapshot files and this gdown command. So you can see the files are getting downloaded. Now, the simulation parameters of the snapshot files are the following. It is a box of 128 kiloparsec H inverse. So, apology, the music snapshots were generated for kiloparsec scale and not megaparsec scale, and that was a mistake. And further, whenever there will be a megaparsec coming up in a plot, it is actually a kiloparsec. After this tutorial, I'll send you an updated Python notebook, which will have links to snapshots of megaparsecs size dark matter distributions. And yeah, you can carry out the same exercise there. So this box size is actually 128 kiloparsec H inverse, and it contains 128 cube dark matter particles. Now, these dark matter particles are just discretizations of the dark matter fluid distribution. So the more you have them, the more closer you are to the fluid approximation. But for the purpose of this tutorial and to speed up the whole process, we'll use just 128 cube particles. You already see that each snapshot file is around 60 MB. And if you try to simulate a 512 cube particle, it goes up to 4 GBs. So that's a lot of space and lot of downloading to be done for the purpose of tutorial. So yeah. So let me also present the outline of how we'll be approaching the problem. So we already have the dark matter distribution from these snapshot files. And with this information, what we can do is calculate collapse fraction. And once we have the collapse fraction, and we supply an ionizing efficiency zeta parameter, you can obtain the number of ionizing photons produced. And depending on the availability of photon, you can find the ionized hydrogen information in each cell. So let us do this step by step in the code. So here, first we need to import all the necessary Python libraries. And I have mentioned what is the need of each library in form of a comment so that you can understand. The most important is the script library, which gives us handle on functionalities provided by script for reionization modeling. So we'll run this. So yeah, once all the libraries are imported, now what we want to do is read the binary data file that music produced. Now these are in gadget2 format. So script already provides you with a functionality in how to read these binary snapshots. And we just have to supply the name of the gadget snap. This is the name of the file that we had downloaded, music snap 002, and it corresponds to a redshift of 8. And outpath is the script files, which means all the data products generated during this run will be saved in script files. All the density and velocity distributions and all the F collapse arrays will be saved in script files. Now, scale distance is a parameter that helps script to know that what is the size of the simulation box that you generated. So if it was it was in scales of kiloparsec H inverse, you just specify 1e minus 3. And if it was in the scales of megaparsec H inverse, you specify 1. Now you can use the default simulation data functionality inside script to set up a class that contains all the simulation data. Remember, we are supplying here the name of the snapshot file, the out path, and we also have to supply the cosmological parameters here. We have to supply cosmological parameters because the gadget snapshot does not contain the information on these parameters. So for the purpose of script, we have to supply these parameters, and we'll set up a class called default simulation data. Let me run it. And I can show you that we can use this to find out what is the size of the box we are dealing with. So if we write default simulation data dot box, so this should give us 128. So that is good. So the all the variables regarding the simulation parameters are set up. Once the dark matter particle information has been set up, what we need to do is calculate the density fields and velocity fields. We'll smooth these density and velocity fields for our requirements. So the box size was 128. We are setting up and the number of grids used to create that snapshot was 128. But we'll smooth those density fields to an n-grid parameter of 64. So that means the effective resolution of each cell would be 2h inverse kiloparsec. And we can use the matter fields class to set up the density fields given the default, the simulation data, the grid, the outpath. And yeah, let's set up the density field information. So once we'll have this density field, we can use this to calculate the collapse fraction for a given minimum hilomass. So yeah, it says that it has already generated the CIC smooth collapse fraction and the CIC default density and velocity fields in the script files folder that we had specified as the output path for our data products. Now, given the density field, what we like to calculate is the collapse fraction. Now, we first specify log10 mmin. Now, collapse fraction is basically the fraction of mass collapsed in halo, which are more massive than the locked-in Mn parameter. So we'll do this through the get f call for Mn. So we'll supply the Mn and we'll get the collapse fraction. And let's print what is the mean collapse fraction for the box. So here the collapse fraction comes out to be 0.04. But what if we take a different value of log10 Mn? So let's try out here. We supply it with a value of 8.5 and try to calculate the collapse. Remember, the F-call array is the collapse fraction in each cell. So when you take the mean of the collapse fraction array, you'll get the information of the mean collapse fraction of the box. This is the output we are taking here. So let me copy it. This goes here. Let's run. So we got a collapse fraction of value 0.03. Now, what happened here? Why did the collapse fraction reduce? Can anyone answer? Are there any volunteers to answer this question? Why did change in Mn parameter reduce the collapse fraction? Okay. So at a particular redshift, the collapse fraction gives the fraction of collapse mass in halos that is more massive than Mn. Now, if you change your Mn from 8 to 8.5, what you're doing is you're not considering collapse mass inside halos between of mass 8 and 8.5. So that's why you end up with a reduced overall collapse fraction. So yeah, so we have already set up the collapse fraction. Now let us generate the ionization and power spectrum plots. Once the matter field is set and we have calculated fraction of collapse mass in each cell, we can compute the number of ionizing photons. Now this will be done by calling the function ionization map. This class sets up the variables required for you to calculate the ionization map. Just a side note, if you go on Jupyter Notebook and just hover around these, the variable names, you'll get what is the description of the variable. So in this, the ionization map was actually inside inside the script module, but you will see what are the parameters it takes and its description. So you have set up the ionization map. Once you have set up the ionization map variables, and if you give what is the effective efficiency of photons, ionizing efficiency, and you multiply it with the collapse fraction, what you're effectively calculating is the a term which is which denotes the photons that is coming out of those halos which can ionize this. And when you use the get qi parameter, what you're effectively calculating is the ionized hydrogen fraction in each cell. So just a point to remember, this ionization map class was set up, and in the default, if you download script, is set up to calculate the ionization map based on the photon conserving formalism. And if you want to check out the excursion set formalism, there is also a provision for that. And for that, you just have to make a slight change, and we'll see that in some time. So let's set up the ionization map and run this to get the ionized fraction of hydrogen. Now once we get the ionized fraction of hydrogen in each cell, what we can do is calculate the mass averaged ionized fraction, and that would mean just multiply this QI array term, that is the ionized fraction term, times the matter density contrast, and run this. So what you're getting here is that the mass average ionized fraction is exactly equals to the zeta times F call. And this is the direct product of photon conserving model. If there is a mismatch, that means there has been a photon non-conservation there. And let us check out if that is actually true by using the excursion set formalism. So you type in method equals to ES to set up the excursion set formalism. And now your ionization map would be calculated according to the excursion set formalism. With the same parameters, let's calculate what is the mass average ionized fraction. So you see that the mass averaged ionized fraction does not match the zeta times F call. So now the argument of the photon conservation is itself intuitive and says that if you have 5 photons, you can ionize 5 hydrogen atoms. But here we see that even though zeta times F call is higher, we are not able to ionize a higher mass. Some amount of neutral hydrogen is still not ionized. So there is a mismatch. For the rest of the activity, we'll require just the photon conservation model. So in the method again, we'll set this to PC and run the ionization maps again, get the numbers correct. And yeah, we have found what is the ionized hydrogen fraction in each cell. Now, given the ionized hydrogen fraction in each cell, what you can also calculate what is the neutral hydrogen content, and that is just 1 minus of ionized fraction in each cell. So this will give you the neutral hydrogen content. Once you have neutral hydrogen content, what you can do is cross correlate this neutral hydrogen content at find the 2-point cross correlations and get the corresponding power spectrum. So let's do that. And here is the code just to plot everything beautifully. So yeah, you just run it and it will give you 3 plots. The first gives you the dark matter density distribution. Second is the neutral hydrogen distribution. And third is the H1 power spectrum. Now, you can see the H1 density more or less corresponds to dark matter distribution. Yeah, you can obtain a power spectrum. Let's see how power varies and the ionization map. So here we were considering just the delta H1 or the neutral hydrogen across the box. Let's see how it varies for different Mn values. Does it have any effect on the ionization map calculations? So here I have written the same code, but it loops at 2 values of the Mn. So one is 8.0 and another I have taken it 8.2. You can take it to be 8.5. Let's run it. And we do the same process of calculation of density fields, F collapse fraction, and getting the neutral hydrogen content, and then computing the power spectra. So what you see is so this is a plot of this is the ionization map plot. So it basically tells you about the ionized hydrogen fraction. What you see is for lower value of log Mn, you get a lower, a higher ionization of hydrogen compared to a higher value of Mn. And this corresponding feature you see in the power spectrum plots too. So let's see how we can explain this plot. I have not included the description of the neutral hydrogen fraction, but we'll get into the paper by Asim and Tirth, and there we are describing the power regarding the power spectrum delta H1. So let's go here. So in the power spectrum plots, what we were actually calculating the power spectrum of was this delta H1 parameter, which is a dimensionless parameter. So this is given by the delta H1, the neutral hydrogen fraction times 1 plus delta NL. This comes from your matter density fields, and divided by 1 minus QH2. Now, once you have a lower mass, halo mass, and it gives you a higher ionization fraction, that means QH2 is increasing. Once QH2 increases, this denominator 1 minus QH2 decreases and the overall delta H1 term increases. That's why for a lower Mn equals to 8, you are getting a higher power. So your power is just scaling up. So this is an effect because at a lower Mn, you are considering more number of halos can form stars efficiently and can contribute to ionization of the IgM, and that increases the ionized hydrogen fraction, and that's why you are the delta H1 parameter, the whole term gets increased, and the power spectrum plots are scaled up. Now, yeah, does anyone has any question in any form till now? Okay, cool. So yeah, now what we'll do next is to generate the same content, the ionization map and power spectrum, but do that across different redshifts. So first we had calculated the ionization map and power spectrum for a fixed Mn value. The next we did looping over Mn, and we generated the ionization map and power spectrum. The second, is there a question in chat? I'm not able to see it.
Yeah, so I can read actually. By Devabhuta Chandra. Could you please show the method part once more?
Method part once more. Okay. Yeah. Let's go to the simpler problem, the first problem itself. So when you are setting the ionization map, you can at that point decide right, at that point decide which kind of method or formalism you want to employ to calculate the ionization map, whether it would be the excursion set formalism or the photon conserving formalism. So here we have written method equals to PC, and that would set up the ionization map, and all the corresponding values of a calculation of number of photons and then distribution of photons would be according to the excursion set formalism if we set it to ES, or it would be according to photon conserving formalism if we set it to PC. So you just have to change method equals to PC to method equals to ES if you want to employ excursion set formalism. I hope that answers your question. Any other questions?
Yeah, he said thank you. So if you have any questions, please ask.
Don't worry about these details. These are just plotting intricacies to get the plots beautiful. And yeah, you can look into it at your free time. But these are the main contents which are separated into different code cells. And the best part of this Jupyter notebook is that you can just hover around at any variable and it will give you what it correspondingly stands for. So for this particular tutorial or any other tutorial, or if you want to code any further, this is a good platform. Try this. Let's just wait some more time for any questions. Then we'll proceed to exercise 3. Okay, let's go to exercise 3. So yeah, earlier I had provided you with music snapshots, and these music snapshots were generated at different redshifts, 7, 8, and 9. We were using just one snapshot to generate all of the ionization maps and collapse fractions earlier. But what we would want to do is employ all the snapshots and see how ionization map varies from one snapshot to another snapshot, and hence what is the effect on power spectrum. So we just do, so I've written the whole code again just so that you get an understanding of it when you look at it in your free time. The first code section just calls the libraries. You set the libraries up, and then you specify what is the data path where you'll find those snapshots. Then you can specify what is the name of your snapshots, and then the out path will basically contain where you'll be storing all the data products of script in. And these are the simulation parameters which will require to calculate the smoothened density field, and hence also the F collapse fraction once you're given the Mn value. And this is the ionizing efficiency zeta. And here are some variables which are required just for the plotting purpose and the looping purpose. Not very important for the tutorial. Yeah, you can look it into later. So we'll set these variables up. Here we have described how we want the plots, and the next part is basically the same codes, but now it is looping over different file names. So it is going to one snapshot, calculating F collapse fraction, calculating the ionization map, and storing the power spectrum or plotting the power spectrum. And then it goes to another snapshot and does the same. So yeah, let's run it. So the best part about script is once you have stored the data product in the out path, it will not recalculate the same things again and again, and will automatically access the saved information. So here it is reading the details of the file which was already created. So once you're done with reading and generating all the density files, the collapse fraction arrays, the ionization maps, you'll result into something this. So I'll tell you what is going on here. When you come to lower redshifts, you're increasing power. And also when you see the ionization maps, you see higher fractions of the map has been ionized. Can anyone explain what is going on here? We are employing the same Mmin throughout, same ionizing efficiency throughout, and we have generated the ionization maps and power spectrum at different redshifts. And we are seeing that ionization fraction is increasing when we come to lower redshifts, and we see the powers is also increasing as we come to lower redshifts. What is going on here? Anyone can feel free to just unmute themselves and answer. It's okay. It's okay to give wrong answers. Like, this is a learning process for all of us.
Yes, please interact. This is the tutorial session, so
Okay. Yeah, so I'll try to answer it for you. So as we come to lower redshifts, your dark matter potentials are growing. And as a result of which, more and more number of halos are coming into mass range of whatever threshold you are setting. So as more halos come, uh, more halos become efficient for producing the ionizing photons, you get more and more contribution from different sides of the map, which are ionizing the neutral hydrogen around them. So basically, with decrease in redshift, you're getting in more contributions from the ionizing halos. And as I have already explained, as the ionization fraction at each redshift increases, uh, we were plotting this particular function, which has a denominator of 1 minus QH2. And as QH2 increases, as we come to lower redshifts, the delta H1 parameter increases, and the power spectrum of that parameter correspondingly scales up. So the power is increasing as the ionization fraction increases. Does anyone have a doubt in that explanation? It seems not. So yeah, maybe we can get into the fourth problem, and let's specify the fourth problem. I've not done it. This is the task for you. So earlier we had generated power spectrum and ionization maps for different values of Mn. And we had also generated different power spectrum and ionization maps for different redshifts. What I want you to do is calculate the ionization map and density and power spectra for different resolutions. Remember the n-grid parameter, which I had specified earlier, that gave you a 2H inverse kiloparsec resolution of each cell. Now you have to vary this parameter and write your code to loop over this parameter. You can just refer to the activity 2B to write the code, and just loop over these grid cells. And as Tirth has explained morning, so the large scale power spectrum, if you employ the ES formalism in the ionization map, you'll get discrepancy in the large scale power spectrum. But in case of photon conserving formalism, you'll see that even if you plot power spectrum for different resolutions, you will get overlap between of the power spectra at large scales. So which should be intuitive. You're just smoothing the density field, so the power spectra at the large scale should not be influenced by that. What will happen is, in the small scales, you are accessing to lower and lower values of K scale with different resolutions, but the large scale power should remain the same. And this is an exercise for you, the 4A and 4B. Do it with the photon conserving formalism, or you can employ the ES formalism and compare it. So yeah, I don't think you'll be able to actually code it immediately right now, but definitely try it. And in a day or two, I'll send the codes, the answer codes, so that you can match to your own exercise, your own results. And if you have any problem, then maybe we can chat on Slack again. Does anyone have any problem? And if you have not understood anything in the whole activity, it's okay. You can ask now.
So now I think it's time for a few questions. What is the Jupyter Notebook and Colab? It is different. What is the advantage of the Google Colab, Divesh?
What earlier we could have used was Jupyter notebooks, and we could have done the same exercise. But the issue of Jupyter notebook is that it is based on your own machine. So it will be using all the library files, all the packages from your own machine. Now, we don't know what kind of different machines all the participants have. That's why we wanted to use a platform which is the same for all the participants, and Google Colab provides us with that platform. So we can use a standard code and run it on Google Colab, and we'll get the same results across without any errors. And so it is beneficial for tutorial sessions, and can be used for collaboratory work. If different people are not working on similar kind of machines, then yeah, use Google Colab.
Yeah, I got it. So basically all the packages, all the modules you can upload in that cloud so that everybody can use. Yeah, I got it. Yeah. So one question from the chat, Anindita Nandi, can you please unmute and ask?
Okay.
I have audios. Okay. So questions from Anindita Nandi. May I have missed? Can you please explain why power spectrum peaks at high K value?
Yeah. So the parameter, so you may see different plots in different exercises. Here I plot the density fields for H1. Now the at these redshifts, large redshifts, so the issue, there can be a discrepancy that we have to handle here. So even if so that may come up when I supply the exact megaparsec H inverse, but I'll try to answer this question. So basically, you're having larger fluctuations in H1 at smaller scales, and this may not be obvious from the plot itself, but the higher power just corresponds to that you have larger fluctuations in H1 at smaller scales, and when you have lower power in the larger scale, it means this fluctuations are dammed out. Even if you have higher overall value of the quantity or amplitude of the quantity, but if there are no fluctuations, you'll not see power in the large scales. And the reason you're seeing power in small scales is because there are larger fluctuations in the smaller scales. Okay.
So I think the power spectra, the peak of the power spectra is dynamic. It should move with redshift. So it basically corresponds to the typical size of the ionized region. So it will not be fixed at large K values. It will move to the smaller K values at reionization process. So it's not a fixed thing.
Right. Yeah, if Varun was not audible to all of you, it was difficult for me to understand him. Maybe he can write in the chat box and yeah.
Yeah.
So
Can you-
another questions from Antara De.
Right.
Can you please explain once more the relation between the grid size and resolution?
So whenever you are working in these n-body simulation codes, what you do is you discretize the whole simulation box into a number of cells. Now, it would be amazing if you can capture all the small scale effects from which are at scales which are tending to 0 to scales which are tending to megaparsec in the same box, but it will be very computationally difficult. So what you do is you discretize the whole simulation box in number of cells, and now the number n grid parameter just gives you how many grids are you choosing to discretize in a particular direction. So suppose if you have a 512 megaparsec H inverse box and you use 512 cells to represent it, that means you have chosen an n grid of 512, and the resolution of the cell would be the box size by the number of cells. So in this case, 500 by 512 will give you a resolution of 1 megaparsec H inverse. But what if you use a 256 grid system? In that case, your each cell will have an increased cell size, and it will have a resolution of 512 by 256, that is 2 megaparsec H inverse. What I mean by resolution here is all the quantities that you're calculating in the simulation box are exact up to the cell level and not for scales which are below that cell level. So if you are having a resolution of 1 megaparsec H inverse, you can calculate all the quantities exactly from 1 megaparsec H inverse to higher scales, but you cannot probe scales which are smaller than that. You cannot exactly say what is going on between 0 and 0.5 megaparsec H inverse. That is not possible. So you're always probing effects which are higher than the cell values, higher than cell resolution. Does that answer your question? Okay.
Any other questions?
If you want to, just some tips, if you want to form your own Python notebooks in Google Colab, just you can add code cells or text cells using this particular two tabs, and this will allow you to type a descriptive text or uh, help you with the executing of single line code. So I can import NumPy in this cell and just run it. So yeah, you can form your own notebooks. and share it among your collaborators. And this is a cool platform.
Yeah, I think no other questions then. Thank you, Divesh.
Yeah, welcome. Yeah.
Your tutorial. So he will be available online in the Slack. So if you have any questions after that regarding installation and also the code, please ask him and he will answer. Yeah. So now we plan to take a group photo. So can I request all of you to please switch on your webcam so that we can take the group photo.
Or I don't see many people. Let them join, and then with YG we can take the group photo then.
Okay,
Because
then
we see only 18 people are there. And
I think let's wait for the 10 minutes. Then before starting the SQL session,
yeah,
we
before
can,
starting the next session, we can have the photos here.
yeah, I think so. So let's wait for 10 minutes then. Yeah.
Yeah, because already some of them are left.
Yeah.
Yeah, you can take the photo about 5 minutes before the session start or something like.
Yeah.
Let them join again. Yeah.
I guess most people will join by.
Yeah, and we can send a reminder in the Slack channel that we'll soon start the special lecture on YG.
Yeah.